What is gravity? Two famous scientists did research on how gravity works. Newton was the foremost of them. What Newton is explaining about gravity is that all things in the universe have mass. There will always be an attraction between two objects, or every mass attracts every other mass. The gravitational force of an object also varies according to its mass. That is, an object with a greater mass pulls a lighter object to its side. The greater the distance between two masses, the less their gravitational force decreases. Force is inversely proportional to the distance to the power of 2. This means that if the distance increases by 2 times, the force will decrease by 4 times. If the distance increases by 3 times, the force decreases by 9 times. This is what Newton explained about gravity. Everything happens just as Newton said. The Earth orbits the Sun, the Moon orbits the Earth, and the universe itself works according to Newton's gravity. If the Sun's gravity is so strong, why didn't the Earth smash into it? Distance and angular momentum are relevant factors in this context. Well, everything's all right. This was accepted by everyone who was there then because it fits perfectly according to physics. But here comes the biggest confusion. The distance between the Sun and the Earth is about 150 million kilometers. Will there be a force for such a distance? For example, if I kick a ball, there is contact between me and the ball. So there is physical contact that makes the ball move. But what lies between the Sun and the Earth is the greatest distance. That being the case, scientists are gradually confused about what the kind of force that causes binding between such objects. And this is where Einstein joins. According to him, gravity is not a force, but it doesn't make sense. Why does it happen if there is no gravity? What's making it happen then? Which mysterious thing causes it? But his explanation for it, though, not understood by anyone at the time, was understood a few years later. And it was that discovery that elevated him to an important scientist in the world. So, what was his discovery? Let's see how that works. Our universe looks like it is empty, but in reality it is not empty. Empty spaces are not really empty. The whole universe is like a fabric sheet. That sheet combined with fourth dimension time becomes space-time. He says curvatures in space-time are responsible for gravity. Let's take a fabric mat, for example, and make a fat man sit in the middle of it, and make a skinny man sit on the edge of the mat. Now we will see that the mat bends inside where the fat man is, so the skinny man is automatically pulled towards the fat man. The fat man does not exert any force, and even if he doesn't touch him, the skinny man is drawn towards him. Similarly, gravity occurs for everything in the universe. As the sun bends space-time, the Earth is attracted towards it. It is not a force. As space bends, it has an impact on the objects on the curve. The mass tells space-time how to curve. Space-time tells the mass how to move. Now it's easy to explain how Einstein came to realize this. He found out the truth through thought experiments. Then the mathematical equations were also confirmed. He's sitting in his office one day when he sees a man cleaning the windows of a building close by. He starts to think about what would happen if that person fell down. While it may seem strange to us to hear this, Einstein describes it as the happiest thought in my life. Let's look at the things that crossed his mind. We will lock the man who was falling from the top of the building into an elevator. A man who is falling will not feel any force, since he is inside the elevator, and there is no reference point. He can't realize if he falls down or floats. The phenomenon of falling down as a free fall without any reference point is like floating in space. That is, according to physics, there is no difference between a person who falls from the top of a building and floats in space. Both of them wouldn't feel any gravitational force. So empty space weightlessness is equal to free fall on Earth. Let's move on to the next step. Now I'm floating in space inside the lift, and there's a ball also floating with me. A motor engine has been fitted to the bottom of my lift, and I started that engine and accelerated the lift upwards at a speed of 9.8 per second square. 9.8 is 1g, the gravitational force for Earth. Now what happens when I accelerate at the speed is that the ball floating with me will fall down on the lift floor, and I will also be pushed towards the bottom of the lift. I feel the same amount of gravity on Earth as I feel inside the lift that is accelerating at a speed of 9.8 meters per second square in space. Whatever can be done with the help of gravity on Earth can also be done in this lift. I don't feel any difference, whether in space or on Earth. So free fall on Earth is equal to free movement in space. Gravity on Earth is equal to 9.8 meters per second square. Acceleration in space. That is, acceleration causes gravity. Now I'm in space inside a lift, and I turn off that engine, and the lift is made to float steadily in one place. What will happen if I throw the ball in straight? When I throw a ball, it goes in a straight line. What if I throw that ball at an accelerating lift? The ball will go down in a curved path and hit onto the floor. So far, everything is going well. Now I've switched from the ball to a light beam. How will it go if I torch the light in the accelerating lift? Light is known to always go in a straight line at constant velocity. If you throw a ball on the Earth, it will travel in a curved path and then fall to the ground. If the ball is thrown from an acceleration lift in space, it will also travel in a curved path. Does that mean light itself will be able to bend? Can light be bent even though it has no mass and always moves in a straight line? Einstein says it will bend. Yes, it is possible if there is something called space curvature, as he claims. How do we find it? The lift that is accelerating at just 9.8 meters per second square does not have enough opportunity to bend the light. So now, I change the acceleration speed from 9.8 to 98. According to Einstein's prediction, end of light in acceleration at 98 meters per second square is very small. That is, it bends only the size of an electron. This means that if we increase gravity or acceleration, light can bend more and more. Well, how do we prove this? In those days, it was impossible to build an engine that had such acceleration and implement it. In fact, not even a rocket was invented at the time, but we have gravity. The sun was the strongest gravity when it comes to our nearby things. Its gravity is 28 times stronger than Earth's because its mass is 330,000 times bigger. If we calculate what will happen in that gravity, the gravity will bend the light to 1.75 arc seconds. An arc second is 360 degrees in a circle, and if you take 1 degree of it, it has 60 minutes within it, and 60 seconds per minute. Of these, 1.75 arc seconds is very small. In 1915, Einstein published his theory with equations. Everyone was confused when they saw this theory. What is this? What is he trying to say? No one understood it at the time. Then 4 years later, Arthur Eddington, the greatest astronomer at the time from England, set out with his team to experiment with this. At that time, they knew the exact location of some of the stars, and if Einstein's theory was correct, the star behind the sun should be visible somewhere else, because the light should bend and be visible to our eyes. They were waiting for a total solar eclipse because the sun's brightness makes it hard to see nearby stars. When the day of the solar eclipse came, Arthur Eddington's team started taking pictures. To their surprise, the stars showed up in the photos in a place they hadn't expected. Gravity had bent light itself because space-time had been bent. For example, I go straight from one place to the North Pole. As far as I'm concerned, I'm going in a straight line. But to an outside observer, I appear to be taking a curved path. Similarly, light always travels straight. Because its path is curved, it also bends. So the shortest path of light can be a curved one. Now you may have a doubt. If the space at the bottom of a massed object only bends, does space bend at the top of that object? All the space-time curvatures we see in the video are shown in 2D visuals, so that we can easily understand them. Its 3D form is hard to understand, but that's exactly the case. It was only after this space-time curvature was demonstrated that Einstein was celebrated as the greatest scientist. This thought experiment is not a simple one. It is the greatest thought in human history. This simply explained not only gravity, but also showed the world how the entire universe works. This is called the general theory of relativity. That's what space-time curvature is. But how did this time come in it? How does space-time explain time dilation? The special relativity theory provides an explanation. We'll see it in detail in the next video.